All right, well today is kind of an unusual day because classes have been canceled due to inclement weather. So this is a little video recording of a very sparsely populated class. Only the faithful few are here. But we'll go ahead and forge ahead because we don't want to get behind. There's one thing I want to, line of code that I want to show you. I've helped a few students with this first assignment. And the question, in the Java program, I want to give you a line of Java code. In the Java program, you're supposed to convert a Java string of characters into an array of integers, and here's the line of code that will do that. B sub I is the integer array, right? So here's how you would do it. Just let me write it out here. So it would be B sub I gets, and then there is a, I told you to use char at. So it would be line dot char at I, because char at takes the ith character. But now this line dot char at I, that is a character, and B sub I is an array of integers. So the way you convert this character to an integer is like this. You see on the number line, the letters of the alphabet are like quote A, quote B. So on the number line, the characters are all on the number line. And over here somewhere else, there's a quote 0, a quote 1. And this line is a line of characters. And these all have numeric values on the number line. And I don't remember what they are. But it doesn't matter. We don't need to know what they are. Let me just make up one. Let's just call it, this is probably not right. I know it's not right. I'm guessing. So let's just say that this is like 86. You know, then this one would be 87, and this would be some other number on the number line. These are just, I know this is incorrect numbers, but we don't need to know what the right numbers are. So what you do is, you see this 0 has the numeric value 86. So you do line dot char at minus quote 0 quote. That's the code. Because what happens is, characters are like, they can be operated on like integers. They are integers. You can add and subtract. That first little example that we did, C example, added 1 to a character and it got the next letter on the character line. Okay? So anyway, like if this line dot char at is 0, then its value will be 86, and you'll be taking 86 minus 86, and that is 0. And if the character is 1, that would be 87, and you would be taking 87 minus 86, and that would be what B sub I would be 1. So that's the way to convert from integers to.
Is it okay if we use parse int?
That someone else used parse int, and I'm going to put a disclaimer in there from now on to not ever use parse int. So no, it's not good to use parse int.
Okay.
And we're going to, we're going to do a lot of parsing when we do our translation program, and we will never use. I will never allow you to use parse int.
Because those are pre-made.
Yeah, they are pre-made, and so it kind of defeats the whole purpose of doing the exercise.
Yeah, I used them on the last two, so that's okay for the last two.
Yeah, okay, but from now on, yeah.
Does the line dot char at sub I minus the 0, does that return an integer, or is that?
Yes. Well, line dot char at returns a character, but characters are integers.
Right. So how does B sub I know that when you do this subtraction that it's getting an integer, not a character?
Because characters are integers in all C-type languages, C, C++, and Java. A char is an int.
So then why would you have to add the minus 0?
Because it would be 86. The integer value would be 86. That's why you have to subtract the character value of the 0. Yeah. This is a little well-known feature of these C languages. You should know this, actually. This is good. Yeah. Well, what we are doing is we are converting the character value 0 to the integer value 0. That's what we are doing. See, if you didn't subtract, if you didn't do this, if you just said caret, then b sub I, if it was the character 0, it would be 86. Actually, we're going to take a look at the ASCII chart right here in a second. Well, I will see what the real number is in a minute. Oh, actually, why didn't I just go look at the ASCII chart right off the bat? Here it is, sports fans. It's figure 3.25. Yeah, let me correct my figure here. What is the value of the numeric value of 0? Do you see the where is the character? Yeah, it's on the second column, right? It's 30 hex. So what's 3 times 16? Is it 48? So this is 48. This is 49. But it doesn't matter what the number is. Don't use the number. Notice this code doesn't have these numbers in it. And it also looks like the lowercase letters are on the other side. These lowercase letters are over here. So I drew the line a little incorrectly there. Recall in figure 3.19 we did arithmetic shift left. What does arithmetic shift left do to the value of an integer? It multiplies it by 2, it doubles it. And then we did, on figure 3.20, we did arithmetic shift right, and what does that do? Yeah, it divides it by 2.
Quick question about
Sure.
arithmetic.
Yeah, that's a good point. That's the good observation because of that fractional part, it rounds. And so if you do an arithmetic shift right of -1, you're going to get -1 again.
Yeah.
Good observation. Yeah. If that's what you came up with, that's correct.
That's what I came up with.
So now these next two operations are called the rotate operations, and they have nothing to do with arithmetic values. And what happens is with the rotate left, instead of shifting in an arbitrary value from the left, instead of shifting in a 0 from the left, you shift the carry bit into the left. And so you see how this is doing a rotate. And these operations are useful in hardware drivers, it's hard for me to give a good example of where this is useful, but it's very common. You should know the difference between a rotate and a shift. All right, so a rotate just, wraps around. So let's do an example. Let's do, now so for the rotates, you have to know what the initial value of C is. Right, so here's one. Let's do, suppose C equals 1, and then we do a ROL, a rotate left of, now let's say we have a 6-bit cell and it's 0, 1, 1, 1, 0, 1. 0, 1, 1, 1, 0, 1. So what will that equal?
1, 1, 1, 0, 1.
Yeah, this 1 will rotate around to here. This will rotate into the C bit. So this will be C equals 0, and then it will be 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, and that 1 from the C will wrap around, and that'll be like that. So does everybody see how that works? And the NZ and the Z, the other bits are not affected. So and then similarly with the rotate right. Now, the next thing we have to do is, next number base we have to learn is hexadecimal. So, answer me this. What would happen if we were all born with 8 fingers on each hand, so we had 16 fingers total? Probably the way we would count would be, we would invent a new symbol for each digit in our hand until we got up to the last one, in which case we'd start back over with a 1, 0. Now, does everybody see how that works? So here's how to count in hexadecimal in this slide. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But 9, we still have some fingers left. So what we do is we use the letters of the alphabet. A is is 10, B is 11, C is 12, D is 13, E is 14, F is 15. And then what's 10? 16. So do you see how to count? Do you see how, what comes after 1F?
2, 0.
2, 0. Here, what comes after 1, 9, F, E? What's the next one after that? What's the next one after 1, 9, F, E? 1, 9, F, F. Now what's the one after that? This goes on. Now, so what's after that?
1A, 0, 0.
Oh, good. 1A, 0, 0, and then 1A, 0, 1. Yeah, good. So does everybody see? We have to know how to count. Does everybody see how to count? It's the same pattern. It's in hexadecimal. And then here what happens is, in figure 3.22, we see that this is just like in binary, it's base 2. So you've got the zeros placed, the 2s, the 4s, the 8s. In base 10, you've got the zeros, the 10s, the 100s. So now in base 16, what do we have? The 1s, the 16s, the 256. Each one is 16 times, each place is 16 times more than the previous one, right? And so here's an example of converting 8BE7 to decimal. So, all right, any questions about how that works? Okay, and here in figure 3.23 is a little table that you can refer to if you want. All this table does is it just counts up in decimal in the body of the table. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then the hexadecimal digits on the top row are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So tell me, what is the decimal number for A7?
122.
A7? 167. Does everybody see that? Are we good? Row A, column 7. So that's just an example of using that. Now, here is the use of hexadecimal. Hexadecimal, and this is an important concept, hexadecimal is nothing more than an abbreviation for a bit pattern. It's an abbreviation. It's just an abbreviation for a bit pattern. That's all it is. Because look, in figure 3.24, in figure 3.24 shows a single hexadecimal digit can represent how many bits? 4. Does everybody see how that table works? So the hexadecimal digit 0 represents the binary digits 0, 0, 0. The hexadecimal digit A represents the 4 binary bits 1, 0, 1, 0. And F represents 1, 1, 1, 1. How many values can be stored in a cell with n bits?
2 to the n.
2 to the n values. And you see that there are, with 4 bits, there are therefore how many values? 16. 2 to the 4 is 16. Is everybody clear on that? So what that means is that since we have 16 digits in base 16, each single digit represents 4 bits. And that's all it is. It's just an abbreviation. So now, let me give you an example of how this abbreviation is used. A couple of examples. Now, suppose we have a 10-bit cell. Okay, so here's an example. So suppose we have a 10-bit cell, and we want to abbreviate 10111001, 101001, 101001, 1100. We want to abbreviate this cell in hexadecimal. So our problem is to abbreviate this cell in hexadecimal. What you do is this. You start on the right-hand side, and you divide up into 4 bits, starting from the right. So you go here, these 4, then here, these 4, and then here, and yeah, and what you do is, if the size of the cell is not a, you know, a divisible by 4 and you have some extras, you just assume these are going to be 0. And then you just go back to this, you just go to this figure 3.24 and write this out in hex. So this decimal equals what in hex? So what letter is this? What is 1100? So this is C, and what's this one? 9, and what's this one? 2. So this equals 29C hex. Does everybody see how that works? That's all it is, it's just an abbreviation. And furthermore, if you have like a 2's complement, you know, if you have a cell that is, and the contents of the cell, you want to represent that as a, and it represents a signed integer, then you include the sign bit in the abbreviation. So you will never have a negative sign in front of a hexadecimal string of characters. Do you see what I'm saying?
Yeah, wait, X.
Yes.
And I just took the whole thing.
You take the whole, yes, that was, yeah, that's what you do. What you do is like if you want to represent a negative value in hex, you write down the bit pattern of the negative value, including the sign bit, and you just include that. For example, if this quantity were to be represented, if this quantity represented a negative and a signed integer, there would be a 1 in the sign bit, and this would be a negative decimal number. Oh wait, I wrote this wrong. It would still be 29C. Yeah. Actually, instead of doing the example that I was going to do, let's just figure out what this number would be. If this, so this 29C in a 10-bit cell, do you remember how would we convert this to the negative value? Remember what we look at? The place value of the zeros. So what are the place values of the zeros? Starting at the right. 1, 2, no 4, no 8, no 16, 32, 64, no 128, but then a what? A 256. Somebody have a calculator? And then another what? Tack on another 1. You remember that? Remember that algorithm? Has somebody done this yet? This is going on film. This is being recorded for posterity, so it better be right.
36.
Say it again?
356.
356? So this number would equal negative 356 decimal if it were interpreted as a signed quantity. Yeah, I think we'll just leave our example at that. Okay, so that's the use of hexadecimal. And here, another way to interpret a bit pattern is as a character. And the code that is commonly used, very widespread, is this figure 3.25, which is the American Standard Code for Information Interchange. It originated with the old teletype machines way back in the early 1900s and has just been carried on since then. And here you can see that in this chart, oh, and by the way, you don't have to memorize this. You'll have a copy of it for each of your exams will have a reference packet, and this will be included. So you'll always be able to refer to this. And you can see, for example, that the capital letter B, what is its bit pattern? 100, 0010, and that's hex 42. Does everybody see how the abbreviation is hex 42? And here we can see where the numbers, the digits, are like we just looked at before. So 0 is at 30, 1 is at 31. And then the non-printable characters, you know, on the left column, these are the non-printable characters, and here's a little what is it on a map? But this is a little legend, or okay, of what those non-printable characters are. And a lot of them, so this CR is carriage return, LF is line feed. That's what's used for the new line character. All right. Now, I want to actually, we don't have time in this course to do this, But you actually should be aware of the fact that this ASCII code is being superseded, especially on the web, with Unicode characters. And there's a description in the text about Unicode, but we don't have time to go through it to describe it in detail. But figure 3.26 shows the advantage of Unicode over ASCII. Unicode characters represent all the written characters in the world, including historical ones, like Egyptian hieroglyphs. And there's Braille patterns, there's Hebrew, Arabic, Armenian. And what happens is the ASCII code, the ASCII chart is a subset of this. So this is a superset of the ASCII encoding. We don't have time to learn about that encoding in this class, but it would be worth your time to read about that on your own. Now, the next little part of a computer system that you needed to do for your homework tonight, there was one exercise, I think, was based on the fact that a bit pattern can store not only unsigned integers, a bit pattern could not only represent a signed integer, a bit pattern could not only represent an ASCII character, a bit pattern can also represent a what? Because all of those things are data. A bit pattern can also represent a what? Have you read about it?
Operation.
An instruction. A machine language instruction. So that's yet a fourth interpretation of a bit pattern. So here in chapter 4, the topic is computer architecture, and the main idea about computer architecture at level what? What level are we at?
3.
ISA 3, is that ISA 3 is binary, and machine language instructions are binary. Now here is what we're going to do for this from now on. You guys have heard of the Java virtual machine? Right? When you program in Java, you've heard of the Java. We are going to study a virtual machine called the Pep9 virtual machine.
What does that stand for?
Pepperdine.
Really?
Yeah. It started off with Pep 1 and then Pep 2, and now we're up to version Pep 9.
Okay, cool.
Yeah.
Awesome.
So this is a virtual machine, and this machine, let me give you a little motivation. This machine was designed to teach computer systems principles. Because what happens is, in a real machine, like the Intel chip or like the ARM chip, there is just a mass of detail that is not of fundamental importance. And I have found over the years that it's very difficult to see the main concepts in a computer system because there's just so much stuff. There's just so many unnecessary details that impede our understanding of the principles involved. So this machine was designed to teach computer systems principles. That's the idea. And it is a virtual machine, so it runs. You will be able to, what we are going to do is we're going to learn the instruction set, the assembly language, and the translation principles, all using the details, all using the features of this Pep9 virtual machine. So now, here in figure 4.1, you recall these are the three parts of a computer, right? You've got the disk, you've got the central processing unit, and you've got the main memory. And what is that called when the input port and the output port actually is wired into main memory? What is that called?
Direct access.
The direct memory access is close but no cigar. Direct memory access is when the information goes from the disk to the main memory and back, bypassing the central processing unit. What is it called? So let's remember. What is it called when the input and the output are wired into main memory? That is called what? Starts with that M. Memory mapped I/O. That's called memory mapped I/O. All right. Now, in the PEP9 machine, so now what we're going to do is we're going to learn the details of the central processing unit and the details of the main memory of the PEP9 computer. All right? So we have to know how they are structured. And here in figure 4.2 is the central processing unit. Now you understand that this central processing unit in figure 4.2 is this central processing unit in figure 4.1, in the middle of figure 4.1. That's where it is in the system. Is everybody clear on that? And this, I'm sorry to tell you, you have to memorize what's in here.
Do we have to memorize the
Everything.
bit length and everything?
Yes, the bit length and everything. So let's go through them. First of all, we have the status bits. But look, we know what the status bits are already, right? Those are the NZVC bits. All right. The next one is called the accumulator. Can you count how many bits are in the accumulator? 16. Yeah, 16 bits in the accumulator. The accumulator is the register. Oh, by the way, these are called registers. The accumulator is called a register. So it's a storage location which contains 16 bits, and that's where the results of your operations are stored. So when you do it, the central processing unit processes the information that puts the result in the accumulator. Are you with me? Then the next one is the index register. Index. Have you heard the word index before?
Operates on arrays.
This is for arrays. The index register stores the index of an array because you have to have a way to process arrays in a machine. It's the fundamental, it's built into all machines, the ability to process an array. The next one is called the program counter. It's abbreviated PC. Now the program counter stores the instruction that's going to, the address of the instruction that will be executed next. PC stores address of instruction to be executed next. Because as you go through a machine language program, you have one instruction after another instruction after another instruction gets executed. So the hardware has to keep track of where in the program you are. Do you see what we're saying there? So that's the program counter. Now the next one is called the stack pointer, SP. Does that sound familiar? Stack, what happens when you execute, what did we study when we studied those C programs when the function was called? What happens when you call a function? You put, yeah, let's review that. Okay, since we brought out, what's the first thing when you call a function? What's the first thing that gets allocated?
The return value.
Storage for the return value. What's the next one? Good. Push the actual parameters. What's the next one?
Return address.
The return address. And what's the next one?
Local variables.
What of the local variables? No. Storage for the local variables. That's 4. And those all get pushed on the what?
Runtime stack.
The runtime stack. So what do you suppose this stack pointer is? It's the address of the what?
Runtime stack.
Of the runtime, the top of the runtime stack. You know, we had the pictures of the runtime stack growing up like this. The stack pointer is the address of the top of the runtime stack. Because all programs have to be able to do recursion and have runtime stacks. So that's in the hardware. Yeah.
Does that limit how like big a stack can be because only 16 bits?
It sure does. Yeah. So the question is, does that limit how big the stack is because there's only 16 bits? And the answer is yes. So this is a very tiny machine for teaching purposes, but in a real machine, no matter how many bits you have for an address, there is a limit, right? Because everything is finite. Everything in a machine is finite. Is everybody clear? And now the last one is called the instruction register. It's abbreviated IR. And what do you suppose the instruction register stores? and instruction. A machine language instruction. Now, how many bits? The instruction register is divided into two parts. How many bits are in the first part, the top of the instruction register? 8, and the next part is what? 16. Okay? Is everybody clear? So just know this. All right? Now, in figure 4.3 is a picture of main memory. Now, here's the thing about main memory, you guys. There is an analogy. You know when you go to the mail room to pick up your mail on campus, where does the service provider go to get your mail? You tell the service provider your what? Your mailbox number. That is your box address. So each one of those bins has a number on it, which is the address. You open the door, and the content, there might be a piece of paper in that box with a number written on it. That number written on a piece of paper inside the box, that's the content. That's a different number than the what? It's different from the address. Does everybody see? Is everybody clear on this? So what happens is each cell in main memory has an address, and the cell at that address can contain a value, a binary value. And the cells are always divided in 8-bit chunks. In other words, how many bytes is 8 bits? It's 1. So memory is byte addressable. And here in figure 4.3, what we have is the first byte is at address 0000. Oh, and by the way, the addresses are always written in hex. So the first byte is at address 0000, the second byte is at address 0001, the next one is at 0002, the next one's at 0003, and each one of those addresses, and it goes all the way from 000 up to what? The last one is what? FFFF. No, you shouldn't, yeah. So the question is, does it actually point to the first bit? It doesn't really do that. It points to the whole thing. Because the data flows in chunks of bytes. So it's not like it points to the first one, like in an array, in a C array. Yeah, question?
Why is it that there are needed 4 different hexadecimal numbers when there are only 8 bits?
That's a really good question. How many? Okay, you understand that this FFFF represents what value in binary? So here, F, 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 F. So what is, but then this is underneath an 8-bit cell. 1, 2, 3, 4, 5, 6, 7, 8. Right? But now if we were to write this out in binary, what would this be? Yeah, this would be 1111, 1111, 1111, 1111. That's the address. That's different from what is stored in the byte. What number is this? How many, can you tell how many bytes are in this memory?
Like in the address?
How many bytes, you see these, each one of these, you see the dot, dot, dot? Mm-hmm. How, if you counted up how many bytes are in memory, how many bytes are in memory? Of the whole thing, including the ones not shown.
65,535.
Yeah, 64K. 64 KIB. It's a 64K memory, 64,000. But each one of those cells contains just 8 bits, you know, like the value in this one could be 011000010. You know, it could be something like that.
And that's not large.
No, well, here's the thing. And this aspect of computers is realistic.
Yeah.
All current day computers are byte addressable. So every byte has a separate address.
They've just grown to be much Like,
Well, there's just more bytes. As technology improves, you fit more bytes in, but each one is still a byte. Each chunk is still a byte. Each byte still has an address. Yeah, and that's been true for decades. In the early days, it wasn't true that they were byte addressable, but nowadays they've converged and they're all byte addressable. Does everybody see that? Is everybody clear on that, on how that works? Now look, you guys, sometimes we write 3 bytes on a line, sometimes we write 1 byte on a line, sometimes we write 2 bytes on a line, just for our convenience. You understand that these are all electronic, and so there are no lines, visible lines, but that's for our convenience. Is everybody clear on this? So we don't want to have to write all of this in binary all the time, so what do? What we do is like in figure 4.4. This is the exact same picture as the previous one, but we just want to draw each line in the same width cell, even though there's different numbers of bytes on each line. Does everybody see what we're saying here? Look, do you see, let's go back to figure 4.3. What is the address of the first byte on the first line? 0000. Now what's the address of the first byte on the next line? 0003. Why is that? That's because there's 3 bytes on the first line.
they're pointing to a specific place in memory and then kind of saying.
And then yeah, so when you look at figure 4.4, those addresses are the addresses of the first byte in the line. Does everybody see that?
And then, so what that's saying is that particular piece of memory or whatever is being stored there runs for.
It runs until it gets to the next address, and you can tell. So how can you tell? How can you tell how many bytes are at address 0003? Well, what do you have to look at? The next address. So what are the ones at 0003? There must just be 1 byte there because the next address is at 0004. How many bytes are at 0004? Well, the address of those bytes must be 4, 5, and 6, because 7 is the next one. So there must be 3 bytes on the line whose first byte address is 0004. Is everybody clear on that? All right. So now this is getting more and more. Now, here's in figure 4.5. Here comes another consolidation. In figure 4.5a, we have the content of 2 cells in binary. Do you see what we're saying here? Address 000b contains 00000010, and then the content of the next byte at address 000c is 11010001. How does everybody see that that's the first thing? Now look, we don't want to write the content in binary either. So here's how you would write the content in hexadecimal. So you see we have at 000b we have 02. Now do you see why that's 02?
It's just 2.
Because 0000 and then for the 0 and 0010 is the 2. And you see where the D1 came from? What's 1101?
D.
That's the D, and then the 0001 is the 1. Now, is everybody clear on that?
It works because they're compartmentalized.
Yeah, they're compartmentalized, okay? Now, does everybody see that this and B really represents what A? Now we're going to take it one more level. The content in a machine language listing on paper or on the terminal is going to look like this. So now the 000b is the address, and the 02D1 is the content. And we're not even going to show the address 000C.
Is that because it's processing it as one?
This is our own convenience. We don't want to have to manually label the address of a string of bytes.
So does that mean the machine automatically processes?
This has nothing to do with the machine. This is our printout convenience.
Okay.
Do you see what I'm saying? This is just I'm showing you, when you look at a machine language program listing, this is how you interpret what's really, you have to know what's really going on in the memory. Yeah.
So like the O2 corresponds to like whatever number is there.
The content of 00.
Corresponds to the next one after.
Yes, that's a very good way of putting it. Yeah, so the 02 in part C, the 02 is the content of the byte at address 000B, but the D1, what's the address of the D1? It's still 000C.
Well, it's just moving on.
Yeah, it's just moving up. That's why we have to know how to count in hexadecimal.
If say tack on. it's-
Yes, however many. You could have 3 bytes. Yeah, 3 bytes is common actually.
Okay, cool. So it's basically just what's the norm of
Yeah,
the standard.
yeah. Okay, now, what did we say the fourth kind of data pattern you could interpret it as? A machine, an instruction. Figure 4.6 is the instruction set of the PEP9 computer, the PEP9 virtual machine. And you see on the left-hand column it says instruction specifier. That instruction specifier is 8 bits. If we go back here to figure 4.2, you see the instruction register down there at the bottom? That first byte is the instruction specifier. That's where the instruction specifier is stored. Now some instructions are just 1 byte long, and some instructions are 3 bytes long. Is everybody with me on that?
And then they just have that address.
But the address is the address of the instruction specifier. Is everybody clear? Now, let's take a look at what some of these instructions are. Now, we're going to learn these instructions later, what they do. For now, you can see that you just look them up. You can look up, from the bit pattern, you can look up what instruction it is. You see what we're saying? So now, what is the instruction that is a return from call? The instruction specifier is 00000001. So if that machine language instruction executes, that returns from a call. The hardware will execute that instruction. Yeah.
How does the hardware differentiate between instructions and like ASCII characters?
We are going to get, that's a very good question. The question is, how does it distinguish between data and program? And we are going to get to that in infinite detail. It's coming up. But now we need to look at these fields now. There is let's take a look at arithmetic shift left R. Now, what does the instruction specifier say for arithmetic shift left R? 0000 101 what? R. Now that R, that is called the register R field. That R is called the register R field. Okay? And what do you suppose that R could be? It could be, because it's in binary, it could either be a 0 or a 1. We'll see what it means in a minute. Does everybody see that's the R, that register R field? Now let's take a look at another one here. What about branch unconditional? What is its instruction specifier? 0001 001 what? A. So what do you suppose that A is? That is called the addressing A field. We'll see what these mean in a minute. Now what about, we have some things here called unimplemented opcodes. Those are trap instructions. We'll explain how that works in a minute, or later. Now let's see, let's take a look at this add to stack pointer. Add to stack pointer. What is it? What is its instruction specifier? 0101 0 AAA. So what do you suppose each one of those A's could be? A 0 or a 1. Okay, so that field is called the addressing AAA field. Okay. And let's do one more. Let's do load word R from memory. What is that? 1100 what? R AAA. So the R is the what? Register R field, and the AA is the addressing AAA field. Does everybody see how that works? Now, all these bits that specify these fields, the bits in front of them are called the opcode. So here's some more terminology. Let's do one with this. Which one did we just look at? The load word R from memory. So if we had 1100 RAAA, 1100, let's do 0101. Okay, so this is the addressing AAA field. This is the register R field. And this has a special name. This is called the opcode. Those bits that are in front, those are called the opcodes. And for your homework assignment today is all you have to do is be able to use this table to identify these fields in an instruction to just look up and report what they are. So these next few tables show how to do that. So here, like I mentioned before in figure 4.7, there instructions come in two flavors. In part A, we have an instruction could occupy both the instruction specifier and the operand specifier. Or in part B, shows the shape of a unary instruction which only has an instruction specifier. You see, so there's two different kinds of instructions. And here in figure 4.8 is how to identify what addressing mode these AAA specifies. So here in this example, what did we have for the addressing AAA field? 101, right? So we look here on this chart, what addressing mode is that? That's indexed addressing. So do you see how to tell that? Use just the table. We'll learn what this means later, but all right, so that's addressing AA field. Okay, and then here in part B of the figure, if we have the addressing A field, in figure B shows how to identify. So if we had an addressing A field of 0, that would indicate immediate addressing. If we had an addressing A field of 1, that would indicate indexed addressing. And those places where we had R's, that's the register R field. So 0 represents what register? No, 0 represents which register in the register R field? The accumulator, whereas 1 indicates the what? The index register. Okay? So here, let's do this example in figure 4.9 and then we'll call it quits. So suppose that we have in figure 4.9 these values. Now, so what it looks like the instruction in at address started address 01A3. Can you what are the first few bits? What are the bits in the instruction specifier? 01111101. So can you remember that? We have to go now. So what do we have to do? So it's 01111101. 011110. No, 101, right? So we have to go back to the table and look at the opcode. So it's 0111. So where's that? 0111. What instruction is that? Subtract from R. Okay. So and so this one has both an R and an A, right? An R and an AAA. So it wants you to subtract from R. This 1 represents subtract from which register? Index register, because that's this register R field. And this is the addressing mode, so what is that?
That's
indexed addressing.
So index to the register.
Yeah, index register, index addressing, subtract from R. And then for your homework assignment, is all you have to do is just identify these with some bit patterns and just do the table look. Just look up from the tables. So it's simple enough? And what all this stuff means, we'll get to that later. But just how it's structured is all we need to learn right now.
And then
Yeah, we usually do them in order.
okay.
Identify the opcode, identify whatever fields come here. Yeah, yeah.
Okay.
Okay, simple enough? All right, good deal. See you next time.